Hi, welcome to another session of Brightex Academy. In today's session, we're going to discuss the concepts of value at risk and how the value at risk can be estimated by normal distribution model. So let's start with the daily returns distribution plot of S&P 500, and here we can see that the returns has been divided in equal intervals, which we call as a bins or buckets. So here the lowest return that the window has captured is minus 11.98%, and the highest return that it has captured has a value of positive 11.58%. So this range has been divided in equal intervals of daily return ranges, and each range is termed as a bin of the distribution plot. So for example, for this bin, minus 0.5% to minus 0.2%, how do we get these values? So here we can see we have approximately 550 observations, right? So on the left hand side we have the number of observations or frequencies. So for this range, for this bin, which has a lower limit of minus 0.5% and upper limit of minus 0.2%, this bin has seen 550 observations. What does it mean is that if we notice an observation that is a daily return of, let's say, minus 0.3%, that falls in this bin, and hence the number of observation will increase from 550 to 551 in the next plot. So this is how this plot has been formed by the daily return data of S&P 500 for several past years. So now that we have understood what is a distribution plot of daily returns, we now move on to the quantification of risk part. So how do we quantify risk? So we can divide this distribution plot in three different zones. If our daily returns are occurring on the positive side, that is we are achieving daily returns of positive values, then we are in the profitable zone. That is, our portfolio will become profitable over the time as we are gaining, our daily returns are positive, so we are gaining values on a daily basis. If we are getting somewhat less negative returns, that is, if we are experiencing negative returns of values less than 2%, then those risks doesn't cause much of catastrophe to our portfolio. That is, those risks indeed decreases the value of our portfolio, but is not devastating by nature. The main factor that creates havoc or that depreciates your portfolio's value significantly comes from these left tail return data, that is the extreme negative returns that's occurring on the left tail part of the distribution. This is the extreme risk zone, and we have marked it with red, and whenever we get a very high negative return like minus 5% or minus 4% daily, then it causes a great depreciation of your portfolio's value. So how do we quantify risk in this part, that is in the left tail of this distribution plot? We can do it by the process of VaR, or defining a threshold of risk. So let's understand now what are confidence levels and how we can associate confidence levels to this daily returns distribution plot. So if you buy and hold the S&P 500 for 100 days, you will see that out of 100 days, 90 days daily returns fall under the range of about minus 3% to positive 3%, and only 10 out of 100 days will fetch a return beyond this range, that is greater than positive 3% or less than minus 3%. So the concept of confidence comes from here. So let's try some examples. So if we are 70% confident, then what would be the daily return range? As far as a plot, we can see that with 70% confidence, we can say that the S&P's daily return will fall from minus 1% to positive 1.3%. What does it mean? If we buy and hold the S&P for 100 days, we'll see in 70 days the daily return value has fallen from the range of minus 1% to positive 1.3%. In other words, the S&P 500's daily return on any given day has a chance or probability of 70% to fetch a value in this range, that is from minus 1% to positive 1.3%. Similarly, we can associate different confidence levels, and as you see the confidence level increases, the range of the daily return also broadens. So for example, we bring up the 99% confidence level, so we see that if we buy and hold the S&P 500 for 100 days, we'll see that it is fetching a daily return from the range of minus 3.5% to positive 3.6%. So this is the actual daily returns distribution plot of the S&P 500 data. But here we will calculate the value at risk by the normal distribution method, and we'll discuss the concepts of value at risk by normal distribution. So we need to have a distribution that can be defined with a normal distribution equation. So let's superimpose a normal distribution plot on this data, on this plot. So as you can see here, the S&P 500's daily return data or daily return distribution plot doesn't actually uh, imitates a normal distribution plot, but here we can see some gaps. And so the daily returns distribution plot from the S&P 500 is more leptocritic. So for this reason, the daily returns or the practical returns of any indices are not even close to normal distribution. Industry professionals usually either tweak the normal distribution equation so that the curve fits the edges, the top edges of the bar graph or the histogram plot, or they manipulate the data, the underlying data, that is the S&P 500's daily return data, so that it fits with the normal distribution curve. But we'll not discuss about it. Let's say from now on that our distribution is normal distribution. As we can see that this distribution is pretty close to normal distribution, but not exactly a normal distribution. So we'll now associate standard deviation with the different confidence levels. So how we can do that? So let's divide this normal distribution into two areas, one with one standard deviation. Here the sigma, the Greek letter sigma, represents standard deviation. So plus sigma means plus one standard deviation, and minus sigma means minus one standard deviation. So a normal distribution by definition has a mean of 0 and a standard deviation of 1. So what we mean by that is that the central tendency of the normal distribution is always placed at 0, and 68% of the observations that is forming the normal distribution plot will have a standard deviation of 1. So here we can see that the dispersion is represented by the standard deviation. The dispersion from the mean is represented by the standard deviation. So one standard deviation has a range of +1 standard deviation to -1 standard deviation. So as we have said, the underlying data that's forming this normal distribution curve, that data's 68% data will fall in one standard deviation range, that is from -1 standard deviation, that is -1 sigma, to +1 sigma. Similarly, we can say that 95% of the underlying data that has formed this normal distribution curve, 95% of it will fall from a range of -2 sigma to +2 sigma. That is, it will fall under a 2 standard deviation range. So this is the formal definition of a standard deviation. In this short lecture, it is beyond the scope that we will be able to discuss standard deviation, but you can subscribe to our channel. We will surely discuss standard deviation in a separate lecture. So as we have seen, the positive part of the underlying data is good for us because it falls in the profitable zone. If we are long on the index, and if the index is fetching a daily positive return, then we are profitable, so we don't care about the positive part. For the negative part, if the returns are less than -2%, that is, the returns are in between -2% to 0%, then we'd say that this risk is under the tolerable range. This doesn't cause much devastation in our portfolio, so we don't we ignore this part as well. But the most important part is the left hand tail of the distribution plot, which carries significant risk and which can uh, decrease the value of our portfolio significantly, as the daily returns occur beyond the -2%. And if we manage this risk well, if we hedge this risk well, we will fetch a portfolio return that is greater than the benchmark return. That is, we'll be able to beat the market or the benchmark if we only control the risk in this tail. So this how do we quantify this risk in the tail? We do that by calculating or by setting a value at risk threshold, and we can do that by the normal distribution approach. So we have zoomed in the left tail part of the normal distribution curve. Here is the formula. We have a equation that describes this equation. From that equation, we can derive the value at risk formula, or the value at risk equation for normal distribution plots with a certain level of significance. And that equation tells us that if we know the mu or the mean, the z value that is known from the cumulative Z table for significance level, we'll see how to calculate the Z values. And if we know the sigma, that is the standard deviation, if we know the portfolio value, then we'll be able to calculate the value at risk at the significance level. X% is the percent significance level. So we have discussed confidence level in the previous slide. So if we take the difference of 1, if we do like 1 minus confidence level, then we get the significance level. So X% is equal to 1 X% significance level is equal to 1 minus confidence level, and X% is the significance level. So for each significance levels, we have different Z values. Otherwise, for this distribution would be, from the sample analysis, we'll be able to calculate the mu and the sigma. And if we know at what significance we want to calculate the value at risk, we'll know the z value, and definitely we will also know the portfolio's value. So value at risk can be quantified by this formula if the underlying distribution is normal. So what are these z values? So if the significance level is 10%, that is x%, x is equal to 10, then the z value is minus 1.28. If the significance level is 5%, then the z value is minus 1.65. If the significance level is 1%, then the z value is minus 2.33. Please note that 10% significance means 90% confidence, 5% significance means 95% confidence, and 1% significance means 99% confidence. So what do we mean by that? We mean that let's talk about this 1% significance level, and let's say the VaR threshold has been placed here. So we can say that 99% of the daily returns will fall in the right hand side of this line of this threshold, and only 1% of daily returns will fall in the left hand side of this threshold, and this region carries a significance of 1% and has a z value of minus 2.33. Now let's bring up the cumulative Si table and see how to calculate the Z values for different significance or confidence levels. So here we have used the confidence level. It's easy to convert the confidence level to significance level by using this equation. This table has been extracted from math.arizona.edu, that is Arizona University's website. So let's say we want to calculate the Z value for 95% confidence. 0.9505 can be rounded off to 0.95 confidence, that is 95% confidence, and 95% confidence level means 5% significance. So let's calculate the 5% significance Z value. So how do we do that? So we see what's the z value here. It's 1.6, and we see what's the decimal z value here. So we add up these two terms, 1.6 and 0.05. So after adding we get 1.65. So 95% confidence level, which is equivalent to 5% significance level, has a z value of 1.6 plus 0.05, which is equal to 1.65. Here we associate a negative term, a negative, because this is on the left hand part of the mean. So for 5% significance, the z value comes out to be minus 1.65. Similarly, for 99% confidence level or 1% significance level, we get a value of 2.3 plus 0.03, which is 2.33, and hence you see 1% significance level has a z value of minus 2.33. So now let's practice and let's calculate the VaR or value at risk by the normal distribution model. So let's bring up a practical question. So assume that the daily return distribution for a company or stock by the name of ABC Inc. is normally distributed with an annual mean of 0.1 and a standard deviation of 15%, and the portfolio value is 1 million. Calculate the value at risk or VaR at 95% and 99% confidence levels. So how do we do that? Let's first calculate the Z values from the table. So for 95%, we know the Z value would be 1.65, and for 99% confidence level, the Z value would be 2.33. That is, we add up these terms, 2.3 plus 0.03 is equal to 2.33. So now that we have calculated the z values for different significance level, that is for 5% and 1%, we are ready to use these values and the given values of mean and standard deviation of daily return to calculate the value at risk by the normal distribution method. So value at risk for normal distribution or by the method of normal distribution has an equation of this, that is minus mu, which is minus the daily returns mean plus z value at x% significance. Here we are using a 5% significance, so z value at 5% significance multiplied, here dot represents a multiplication, dot sigma, which is the standard deviation of the daily return, which is given as 15%, and we multiply this whole term by the portfolio value p. So if we input these values from the problem statement and the calculated z value for 5% significance, we get a value of US dollar 147500. So what does it mean is that, so this is a value at risk at 5% significance, and the value has came out to be $147,500. So it means that there is a 5% probability that the daily minimum loss will be 147,500 US dollars. Similarly, value at risk at 1% significance by the method of normal distribution can be calculated by using the same formula. All the input values remains the same except the z value, because the significance level has changed from 5% to 1% here, so we have to use the z value at 1% significance, which we calculated to be 2.33. so instead of 1.65 here, we have used 2.33, and after calculation we get a value of 249,500 US dollar. So a value at risk at 1% significance with a value of 249,500 US dollar means that there is a 1% probability that the daily minimum loss from this portfolio will be 249,500 US dollar. So this is how we quantify risk. We measure risk very precisely by, actually we don't measure risk, we measure the threshold that the daily loss will be minimum this much. So this is how we quantify risk with the value at risk. We can also estimate the actual risk with that a portfolio faces with a certain probability, and that can be calculated using the expected shortfall method, which we will discuss in the upcoming session. So here, as you can see in the problem statement, we have used the daily return distribution, and the mean and standard deviation is for the daily returns, that is daily returns mean value is 0.1 or 10%, and daily return standard deviation is 15%. So what if we are given with the distribution of, say, profit and loss, or if the normal distribution is actually a log normal distribution, then we have to use different formulas, different equations to calculate value at risk. Let's see those formulas. So this is the formula that we have used just now, that is value at risk uh, for normal distribution at x% significance is equal to minus mu, which is the mean, plus z value for x% significance multiplied by the standard deviation sigma. We multiply this whole thing inside the bracket by p, which is the portfolio value. We use this equation when mean, mu, and standard deviation sigma are given in terms of daily returns. Now, if the mean and standard deviations are given in terms of profit or loss, then we use this formula. This is a more simplified version. We don't use the portfolio's values because inherently all the information has been captured by the mu and sigma, that is by the mean and standard deviation, if it is provided in terms of profit and loss. Now again, this is for normal distribution, but what if the underlying distribution is not normal but is log normal distribution? If you want to know what is a log normal distribution, please keep in touch. We will upload a separate video explaining log normal distribution in coming sessions. So value at risk by the method of log normal distribution, that is when the underlying distribution has a log normal characteristics, then for x% significance, the value of the value at risk by this method can be known by this equation, where we multiply this term by the portfolio value again, and here the log normal, uh, this is the e value or the exponential to the power the mean minus z at x% significance multiplied by the standard deviation, and we take 1 minus this and we multiply this by the portfolio value to get the value at risk when the underlying distribution has a log normal characteristics. So this brings us to the end of this session. In this session, we have calculated the value at risk by the normal distribution method. We have seen what is a normal distribution. We have understood what are confidence levels, and we have also known how standard deviation can be associated with confidence levels, how we can use standard deviation mean and the z value to calculate the value at risk. We have also learned how to use the cumulative z table to get the values of z's or z's for different significance levels. I hope you learned something new today. If you have any queries or if you have any feedback, please feel free to write us at brightexacademy@gmail.com. So if you have liked this session, please also give us a thumbs up, and please subscribe and share with your network. Thank you for your time. See you in the next video. Till then, goodbye.